Have you ever wondered, after a Git commit, how does Git know exactly which files changed and which didn't? The answer is hidden in a data structure called the Merkle Tree. A hash function takes data of any size, like a file, and produces a fixed-length string called a hash value, a fingerprint of the data. Key property: change even 1 byte of input and the hash changes completely, and you cannot reverse a hash back to the original data. Our repository has 4 files. A, B, C, D, Git computes a hash for each file. These hashes become the leaf nodes of the Merkle tree. Each leaf node uniquely represents its file's content. As long as the file stays the same, the hash stays the same. Combine adjacent leaf nodes in pairs. Concatenate HA and B, then hash them to get the intermediate node HAB. Same for HC. Combine HAB and HCD to get the root node, root hash. It is the unique fingerprint of every file's content in the repository. Suppose we modify file cgit recomputes HC and gets a completely different value. Let's see what happens next. The change propagates up. HC changes, HCD changes, the root hash changes. Compare just the root hash, and Git instantly knows if anything in the repository changed. Every Git commit, Git builds a Merkle tree for all files at that moment and stores the root hash in the commit. Multiple commits form a chain. Each commit points to the previous one and holds the state fingerprint of the entire repository at that moment. This is how Git permanently remembers every change. The essence of the Merkle tree, hash functions, compress data into fingerprints. Fingerprints are combined layer by layer until a single root hash represents all content in the tree. Git, blockchains, and IPFS all rely on Merkle trees to verify data integrity. Change 1 byte, the root changes, and no tampering goes undetected.